Anna Hoffman, and welcome to this episode of Data Exposed Live, especially Something Old, Something New, where I'm joined by Buck Woody. Buck, thanks for joining us again today. How are you doing?
I'm doing great. Hey, listen, before we get started, I know we had a bit of a kerfuffle last time. You know, I had the green screen you told me to use, and then you said I shouldn't be using a green screen. So anyway, I have the other thing that you told me to get. So I have that right here.
Wait. What is that?
It's the coffee filter. You told me when I'm on camera, I should use a filter to look better. I don't know how that works, but
yeah,
I have it just in case.
That's not how that works, but that's okay. Hey, you know, it looks like you got a chicken on your shirt. What's going on there?
Oh yeah, this is today's math shirt.
I had a hen who could count her own eggs. She was a math chicken. Where do you come up with these things?
Yep, every month we're going to have one every month. Anna.
Well, we're happy to be here today. You know, for everyone joining us, this episode is called "You Have to Draw the Line Somewhere." So we're going to be talking about regression, which is going to be exciting. And I wanted to say that from wherever you're streaming from today, be sure to let us know if you have questions. Whatever those questions might be sure to put them into Learn TV or from wherever you're streaming, whether it's Twitch, Twitter, YouTube, some other streaming platform I didn't realize we were streaming to. Go ahead and put your comments in, say hi, make fun of Buck with me, ask questions, whatever you want to do.
Yeah. And, you know, Anna, today, one of the algorithms we're going to talk about, both in your segment and in mine, involves predicting one of two things. And that reminds me of the time I went and I bought some new gloves.
What?
Yeah, I opened some gloves that I'd bought, and it turns out they were both lefties. They were both lefts.
Okay. Not really sure how that relates here, but okay.
Yeah, I mean, on the one hand, it was great, but on the other, just wasn't right.
Oh my gosh. These dad jokes, man. Okay, well, anyways, we also wanted to share that there are a lot of learning resources for you that are available if you're looking to learn more about data science. There's this thing on the Microsoft Cloud Skills Challenge called the Azure Data Scientist, and just a quick glance at that, you can see it's called 30 Days to Learn It. And basically you can register. And once you register, you can pick a different path. We were kind of suggesting the Azure Data Scientist path because it's most relevant to what we try to talk about on this show. But if you get started, you basically have 30 days to go through a set number of learning paths. And then if you are able to get through all of it in the 30 days, I don't know why I want to say 30 minutes.
I think you've had a lot of caffeine, and so you're trying to hurry up.
Really fast. But if you get through it in 30 days, then you're going to get 50% off your certification. So you can come in here and learn more about that. We'll put a link back up on the screen, aka.ms/30 days to learn it/data is where you can get to this one. You know, everyone takes a different path to learning data science. And I think Buck and I both have different paths. You know, Buck, right. How did you learn data science?
Yeah, so it kind of grew up for me over time. When I started in this field, there wasn't, the term wasn't used, right? So in fact, in the 70s, the algorithms and things that we used back then, which were more expert systems and fuzzy logic, that sort of thing, that actually has a term now, which I'm a little offended by, called good old-fashioned AI. That's literally its technical term. And then you went forward and you became a researcher. That was a thing you would do, or an analyst would be another thing you could do. And you had a sort of a background in statistics, which I talk about on the show. And then as these new technologies came out, late 80s, early 90s, and then really maturing in the 2000s, you started being able to deal with these larger sets of data. We ended up with these new tools, some of which you're showing. And when you had these new tools, they allow you now to add in sort of the programming to the statistics. And then, of course, you have a domain knowledge, meaning you know a lot about finance, or maybe you know a lot about oil exploration or whatever it happens to be. And those three things sort of make a data scientist. So I came into it by sort of growing up with the technology, but you took a different path.
Yeah, and I think it's important to call out that anyone, it's, we say it's data science, but at the end of the day, it's not rocket science. So
That's
I think that regardless of your background, this is something that most people can tackle. For me, I got really interested in it. I did something similar to this Azure data scientist. Back then it was called like the Microsoft Professional Program for Data Science. Kind of got my toes wet and was like, you know what, I'm going to go get a master's degree. And getting a master's degree and working full time, very difficult, but it's over now. So here we are. But
I remember
anyways,
those days. I remember those days. You were, in fact, that was back when we were still traveling in the before times. Before
times.
Yeah. Hey, listen, we need to cover something though that's kind of important. On the show last time, I displayed something that had become a point of confusion. And I had designed this very cool logo, which you can see here. It's just an amazing, it's the best logo. But apparently there were some discussions, specifically, we didn't reveal this last time, around you and Bob Ward, around this item in the logo. And I asked, so what do you think this is then? Is this Buck's beard? Is this Buck's head? Or is this the shark mouth from the movie Jaws? And I was befuddled that you all didn't agree with me as to what it is. So we ran a poll. We needed to settle a bet. Now, we didn't tell anybody whose choice was whose, but we needed to settle a bet. So Marisa, our producer, ran the poll. Marisa, do you have those results handy?
Yes, I do. So A, Buck's beard received 30% of the vote. B, Buck's head received 40% of the vote. And C, shark mouth from the movie Jaws was 30%. So I think choice B, Buck's head, is a winner. And I think that's Anna's choice. So Anna.
Yeah, sadly, that was Anna's choice. Oh, I wondered why your head looked like that. And I'm like, we've been working together for like 6 years. You think my head you think I have hair?
Well, that's why I was confused. I was like, oh, we're in this imaginary world where you have hair on the top of your head.
Okay, whatever. Anyway, to remove any confusion, we have redesigned the logo. Hopefully the glasses matching Anna's glasses helps clear things up at least just a little. As always, you can make comments during the show, but on the Learn Live, or rather the Channel 9 experience. So if you're on one of the others, you can pop over and make comments in that area. Well, let's talk about today what we're going to talk about today. It's all relative. Everything relates to things. Anna, when we talk about machine learning, as I mentioned earlier, it actually came from sort of statistics and the unholy marriage of statistics and programming sort of coming together. And this comes even further back than that. We often know that things will happen sort of at the same time, or maybe right after each other. And sometimes we even wonder if one thing causes another. For instance, people who work at a company a long time generally get paid more money. But is that always true? Well, there's an old Greek statement that says ad hoc ergo propter hoc. It means after this, therefore because of this. And that's not always true. I'm going to pop out to an interesting website here. So this is a site where a gentleman went through and he took numbers that happened at the same time. And this is a statistical formula called correlation. And correlation just means at the same time or with one another. That's all those things mean. And he took some numbers, and so he began to calculate the correlation, which is a thing you can calculate, of two events happening at the same time. For instance, I give someone chocolate and they smile. The giving of the chocolate caused them to smile. So he went and looked at some other things. So here's one. The number of people who drowned by falling into a pool correlates 66% of the time with the films that Nicolas Cage was in. I thought that was kind of interesting. Another one that's very interesting, and he's got numbers behind all of these. The per capita cheese consumption correlates with the number of people who died by becoming tangled in their bed sheets. I can't even imagine that, that this is a thing. And Anna, I think you tweeted earlier that the divorce rate in Maine correlates with the per capita consumption of margarine by 99%. So the more margarine we eat, the more people in Maine get divorced.
It's pretty crazy, but I do kind of like that we're trending downwards on both of these items.
That's a good sign. Now, this one is obviously my favorite. The age of America correlates murders by steam, hot vapors, and hot objects. I don't want to know what any of those things are, but it is kind of interesting that those things correlate well. So coming back to our idea here, relation does not mean cause. Causation is not caused by correlation, and correlation is not causation. We're going to need some of the math we talked about in our first episode. If you remember, we did a little, remember I talked about how important math was to all this. We're going to need a little algebra. We're going to need a little statistics, and we may even sneak in some calculus sort of here and there. And this helps us understand the relationship between cause and correlation. It helps us to get that. But Anna, it gets worse. I found this white paper at night when I can't sleep, which is pretty much every night. I read white papers about, I'm fascinated by quantum mechanics and the world of quantum mechanics. Well, there's a new paper out from the Center for Quantum Computation in Oxford in the UK back in 2008. And they actually came up with 5 quantum axioms, which you can build information on. And their 5th one rules out classical probability theory. Do you know what that means? Do you know what that entails?
Well, I mean, it can't be suggesting something alternative to correlation doesn't mean causation.
Well, it's kind of interesting. They've proved, and you want to get into some math, you can go through the 700 pages that are in here, which I did. That's how I go to sleep.
Wow.
But if you do this, like if you drop a cup and then it breaks on the floor, we kind of know that you're dropping the cup caused it to break, right? I mean, we can show that. This 5th axiom says you can actually have the reverse, which means the breaking of the cup caused you to drop it. All right, we're not going to do that today. That's probably
that sounds like some Twilight Zone type of stuff.
That sounds like we shouldn't do that. So here's what we're going to do. We'll do a lesson someday on quantum machine learning. Now, many machine learning algorithms that we're using that you're going to show have a very simple set of formulas to do predictions on one of 2 outcomes. A thing is in a category or it isn't. If you drew a group of things, you could put a line to divide them. And then on one side, a thing is part of the group, and on the other side, a thing isn't. You can also use another formula to predict the next value in a series of data, like weather, right? And the stock market, the stock went up or that sort of thing. And so we can infer a further value from current or past values. And for this type of prediction, we could just use an average to predict the next observation. And I think today you're going to actually show us just trying to use the average and just taking a look. And it doesn't really work, right? So if I get a quarter and a dime and a nickel and another quarter and so on, if I just average those, that doesn't predict the next value very well. So what we can do is we can use a little algebra and we can take a line that more closely fits the data that we have. But we need to do that in the best possible way. So we take a formula that takes into account the slope. Remember the slope of the line? Y equals mx plus b. Remember that from school? That was what, high school for you was what, last week?
Rise over run, yeah.
Right, that's right, yeah. And so we can take that and then the intercept. Remember that? Are you having flashbacks now? The intercept stuff. All right. Well, we can actually take that and there's another formula. And you can see I've got it here. Now, this brings up something that becomes kind of interesting in statistics. A lot of times they'll just start switching the letters around, and sometimes they matter and sometimes they don't. So you may actually see this formula written as y equals b plus mx. That's fine. This is actually called the general logistic model, or GLM. And then this general linear model formula, we probably need to define a few terms here. So let's take a look here. Number one, we have the y, and that's what we're trying to predict. Some people call this the response. And basically, this is the dependent variable. This is the thing that we're going to be able to take that line that you see there and go all the way out even further without any data on it and make a guess. That's the guess. The y is the guess. And again, this is for things like stocks and so on, where we want to predict a value from past values. And that's why it's called a linear or line model. And then down below that, you can see the slope. You remember that. And that's actually called the coefficient in this general linear model. And then down below that, we have the intercept and the constant, sometimes it's called. And this is the general model, but we're going to need to add in an error. We'll come back to that in a minute. That's also called a residual. We'll come back to that in a moment. All right. So the final thing we have is our inputs, the things that are driving it, right? So going back to our lines here, we said our hypothesis was that the longer you work at a company, the more money you should make. And we see these are just plots of X and Y's that we sort of see here. All right. So if we have all that, we can now create that line and using our formula, and it'll be straightforward and it'll be pretty easy to do. Now, you're going to show us how to do this much simpler. I'm just going to show you some of the hand calculations you can do. We'll do this from time to time, but we'll quickly get out of what you're even able to do by hand. It gets a little more complicated than that, more complicated than we want it to be. So we'll be a little quick here, and we'll maybe be a little overly simplistic. But there are a couple things to know here. Is there are simple, which is one variable. So we've got salary on the left there and years worked on the bottom. So that's just one variable. We're predicting the salary, but we're only doing that by years worked. Or you can use multiple linear regression, which says we're going to use lots of them that are doing that. Okay. All right. So I think we've got some terms defined. You're not lost, yep. Right, Anna? You're tracking.
Not yet. So just to clarify, the years employed is going to be our independent variable, and our salary is going to be our dependent variable.
There you go. And you know why they're independent and dependent, right? Does that make sense? You know why they're dependent and independent. The dependent variable depends. The glass breaking, it depends on whether Anna dropped it or not. Does that make sense?
Right.
That's
Yes.
the way you can think about it. So forget the independent variable. That kind of feels weird to say something like that, but dependent is pretty obvious. If you say, I'll give you some more coffee, but that depends on how nice you are to me, right? that right? So we get that.
Sounds about
okay.
right. Yeah.
All right. Now, I did want to ask you a quick question here. So we've got years in the company and salary. We should be able to predict your or my salary that's coming in the next year simply by this one variable, correct?
Well, maybe.
I mean,
seems like other things might lead to that just
like
besides.
What? I mean, like what? I mean, obviously attractiveness. I'm going to, get a little more, but I mean, I'm trying to keep that out of the equation.
Yeah, I mean, maybe your position matters. So if you're the CEO versus me, your years at the company might not matter.
Right. So maybe the person that comes in as CEO has been there a year and they make a lot more money than we do. So it looks like simply from just asking that one single question, do we have enough information? The answer really here would be no.
Yeah.
Right. We would definitely not be able to do that. That in my mind is the first thing. And we actually covered this in our last episode, you remember, on exploratory data analysis. And I think you even showed that you can use data science to find out what things you need to keep to do data science. We can actually predict which of these variables work.
Which
right?
features are going to be important. And
That's
I would
right.
think this isn't an important feature, but not the only important feature.
Yeah, it's all kinds of interesting. For instance, remember you and I used to teach together, and when we would teach, we would bring up what would predict that someone will be a manager. And we would ask people, what do you think? And no one ever brought up two things that seemed to, that we had two reasons for. One was height. Remember that? We actually did some analysis, and taller people are managers more often. Remember we saw that? That was kind of
that
weird.
was an interesting one.
Yeah, it's not good. That's not saying it's a good thing, but it's actually saying that that's what that was. And it was eye color. Remember that? Because we have a predominant eye color on the planet. There will be more people of managers in that eye color than there will be in other eye colors, simply because there are more people with that eye color, which is kind of interesting. And in fact, you have to weight the eye color, because if you do see someone that's like 10% of the managers and they have an eye color that's not represented by 10% of the population, they're overrepresented. So we actually have to be very careful. And in one of our episodes, we're going to talk about bias. By the way, what is the least common eye color, Anna?
Green?
Yeah, green is the least common eye color by a lot. Most people say blue, but blue is actually not that unusual, which I found very interesting. All right, well, that's got nothing to do with anything. What things do have to do with is we're going to try and fit this line. I think you can see you can see my mouse here, but I'm going to draw a little bit on our screen. So let me pop up a pen here. We try to get a line that goes through most of the data if we can. We want that line to fit most of the data. If we just connected them, it'd be this horrible jumble. If we took an average, it won't be right. So we've got to figure a way to get the line to go through most of the middle of the data. And we do that by figuring out this distance here. You can see this distance here from the algorithm as it plays through. As we start playing through this algorithm, we want to see how close that this gets. And this is actually called an error. It's actually called an error. And when we think about this cool dude here. This guy,
oh my gosh,
I know, right? And this is a real picture. This is like somebody really drew this picture. It's not like a caricature at the carnival or something. This guy, this is Adrien Marie Legendre. He was not a fun guy to bring to parties. I'm just being honest here, right? I mean,
you were there, right?
I was there.
When was this?
I mean, honestly, how would you feel knowing your job is essentially doing high school homework for the rest of your life? But anyway, I digress. I mean, I regress. Anyway, he created this thing here called the least squares method. And basically, this is a mathematical calculation that helps in our linear regression measurements. It takes the mean value where the independent variable doesn't even exist. We basically draw the intercept, a straight flat line, and we take the mean value of that away from the regression line itself, the slopes. It then takes the differences, we call these errors or residuals, and it puts the line using calculus to reduce that difference. And you can probably see what I did there? Probably. Anyway, you can probably see that those outliers really affect how the line lays out. So we've got this grouping is not very tight. So if you have a CEO that's making millions, and we're down here in the $10,000 range, we may not even want to include the CEO in this measurement because it's just too much of an outlier. So you recall in our EDA last time we did this. All right, now there's a lot more here that's very useful. Not only can we use this line to predict the next value, we can calculate a value called R squared to see if the independent and dependent variables even correlate well, and another number called the p-value that will tell us if the R value is useful. and how useful it is. And you can learn all about that in the links for this episode on our GitHub. I tell you what I want to do, if you don't mind, Anna, I'm just going to take a couple minutes here, and I'm just going to walk through the steps I did to get to that. So it's actually not that hard. The first thing I did was I just got our salary and our years employed, and I just got this data. So I've just got that here. And
you just
then
got it? Where did you get this data, Buck?
From an HR database.
Okay. Well.
Yeah, it's not important.
Okay. All right.
It's not important. But by the way, your training, you need to get your training done. Anyway, it's marked as not being complete. All right. So all I did was I did some math on these things. I did some sums of things, and then I did a few other pieces of math. Very simple. I multiplied the X and Y. I squared the X value, I squared the Y value, and then I just summed all that up. Now I'm doing this in Excel just to save us some handwriting time, because obviously when we get, we've only got 73 or 74 values here. When I get like into the tens of thousands or millions of values, this is just no way. Then I just plug those things into the formula to find the M and the B. Very straightforward. And it's much less difficult than it looks. This merely means sum. I think we all know that. We take the sum of y's, and I've done that right here down at the bottom, times the sum of the x's squared. I've just done that down here at the bottom, minus the sum of the x's, which I've done down at the bottom, over the sum of the x's times the y's. So I've just done that right here. So all I've done is just sort of plug these in. Same things here, the number of observed values, the X's, the Y's, not that big a deal. Here's what I'm trying to get across, not these formulas. Who cares about these formulas? That's not the important part. The important part is it's just math that you build up, and it's no more complicated than addition, subtraction, multiplication, and division. That's it. That's all that's in stats. You're going to square things or take square roots, but that's just multiplication and division. It's very simple. It's just a lot of it. And unfortunately, some of these formulas, as you well know, they'll use a letter, which means add these 4 formulas together. And then when you go to those formulas, they have a letter, and you have to add 10 values to make that. And they have a formula, and so on. So it's a nice compact notation, but it can be nasty. All right. So then step 2, I just find the M and the B. That's from our formula, from our original thing. Once I find them, I can simply plug them into Y equals A plus BX. That's it. That's it. That's as hard as it gets. So by hand, it's not that big a deal to do this. And that is this formula that we saw is sort of, right here. That's this formula right here. So that is linear regression. And this thing is so incredibly powerful, and you can do it by hands. By the way, you don't actually even have to do it by hand. Even if you're using Excel, I simply made that same data, and I did a thing. I added in the solver. There's 2 things you can add into Excel just by clicking a button. I added in solver and data analysis. I clicked solver, told it to use the data table, and it popped out and did all of that work and did the plot for me. Did all that work and just really quick, and can tell me, remember that R value I told you about, and all these other things that you can get to see. So it did all of the work for me and got all of the errors, those residuals. It did all of this work for me, easy peasy, quick like a bunny. All right. Okay, so that's linear. This predicts a continuous value. So I could theoretically say, if you worked at the company 40 years, even though we've only got 19 years of data, theoretically, if I do everything right, I could predict year number 40 with some level of certainty. So the linear regression model, which is the first in our general linear models, predicts continuous variables. But wait, there's more. How much would you pay for this algorithm? But wait, there's more. If you order today, you can actually get a second algorithm for the same price. And in this algorithm, we're going to do logistic regression. And linear and logistic, that's kind of an interesting dual thing there, right? You see Sigmund doing his linear and logistic deal. And you know what logarithms are, right? You're familiar with logarithms?
Oh, yeah.
Okay. All right. So logarithms help us develop curves. You'll see them used a great deal in curves. And here's what is happening in this rather simplistic looking formula. This is kind of you're like, oh, well, that looks much easier than the last one. Actually, it's way worse. It's so much worse. It is so much worse. It is so much worse that it's almost impossible to do by hand. Like, almost impossible. So linear regression works by creating a line you can follow to predict the next value of something. Logistic regression works by predicting whether a value is in one group or another. In a way, it kind of divides out the data by boundaries. And it does this by forming this curve, this S-looking curve called a logistic curve, right, that we get there. And basically, it's going to build on the linear regression formula. It's actually going to use it in one of these numbers, actually takes into account the formula we just did, but it's going to generalize down to a true or false or 0 or 1. It's two things. Now, once again, be aware there's variations on all the formulas I'm showing, but we're going to keep it as simple as we can for now. I just think it's so cool that one family of algorithms can do two totally different things. For logistic regression, we get a measurement of the relationship between the dependent variable, the thing we want to predict, and the independent variable, the things that help predict that, by using a logistic function. We then turn those probabilities into a 0 or 1 based on a threshold. And this is using something called a sigmoid function. You can always think of sigmoids as S's, and it's an S-shaped curve. And that way it's still linear, but it's a curve linear. All right, remember that in linear regression, we used least squares. Our buddy Marie, I think he looked like that because his middle name was Marie, but whatever. We used least squares, but in logistics, we're going to use something called the maximum likelihood. And so now we're dealing with probabilities and guesses. And then you compare that to the values you have in the data. You do it over and over, multiplying all these out. That E minus X goes on forever. And then you do this over and over, move the S curve until you have the maximum likelihood for the prediction. And once again, there's formulas on top of formulas on top of the formulas. So hit up the links in the GitHub for more detail on this. There's more math here.
Buck, if I could interrupt you just to kind of take a step back from what we're talking about. To me, when I think about linear regression versus logistic regression, with linear regression, you're trying to like find a value, right?
That's right.
How much money are you going to make? And with logistic regression, you're almost doing, and many times you can use logistic regression for doing classifications.
That's exactly right.
And using this maximum likelihood to understand like, oh, is it more likely to be a fish versus a dog, if you're doing some sort of animal prediction or that sort of thing. So I, just stepping back and taking a look at what this really
very
is
good
for.
point. And not only that, you will show us later in other episodes that this is not the only classification algorithm. By the way, most data scientists start with regression. You should really start there. It's very important. I'm going to show you an example again in Excel and even R, and then the machine learning libraries that you're going to show are going to do the heavy lifting. The most important bit is to understand that the power of regression, their limitations, and which one to use for what, just like you just said. As we talked about earlier in another episode, the most important part of the data science process is to really understand the question you're trying to ask. So let me do these two things, and then I'm going to hand it over to you so you can show us how to do it even easier. Here's that weird formula again. This one has these 6 steps. We calculate what's called the logit. I've heard it lots. What do you say?
I say logit.
Logit, me too. But I think I've heard just about every kind of. Anyway, this is a value. It's a kind of formula. So I've got 3 things here. This is something I want to predict. And these are 3 things I know about it. It doesn't matter. This could be years at the company, grade and pay, skill level. I don't know. It doesn't matter. These are just some values I want to predict. And this, I want to predict yes or no, right? Am I going to get a raise this year or am I not? Something like that. So I calculate this formula first. There's a big formula in there. And then I take the E hat of that and I get the exponent. And then I can use that to calculate the probability that that will happen. And then we're down to something called the log of the likelihood. This is that guess that puts it in the S or on the top or bottom. And now what I can do is that gives me these three things that I can use finally in my formula that actually works. And now I can simply change some values and I'll see, am I going to get a raise or am I not going to get a raise, that sort of thing. And it'll predict for me how that works. I took your cue on this cool program you showed me, this Azure Data Studio thing.
Very cool.
I put my R in here this time. I just added a few things, some libraries that I needed. And then I went after an India data set from the Pima area where people get diabetes fairly frequently. And so you want a lot of positive values of something so you can test it well. So these folks, unfortunately, turned out to have a high rate of diabetes. So they take that. The original one, by the way, had some flaws. So there's a new package in R that corrects some of those flaws. And all I did, and I just wanted to show you this part right here. Right there is the general linear model. It's just a general linear model of the data of this by the train data, which is the training and testing that I did here. And I'm just looking for a yes or no, and then I can simply predict with it. And then I get this cool graphic that you see here. This is that graphic you saw on my slides. So the point is doing logistic regression by hand, not really feasible to do. Better to use tools to do that. And based on that, Anna, I think at this point, I've kind of shown the two parts of math that you can use for linear regression and logistic regression. Would you have some examples of doing that, say, in machine learning that might not involve quite so much paper and pencil and calculators?
Yeah, definitely. I mean, I think this has been really valuable, and I'm even going to revisit most of your examples and show you how I've been doing it or can do it differently using something like Python or even Excel. So with that, let's talk about getting linear. So I'm going to put up my screen and, you know, we want to take a look again at this example you had of having your years employed and trying to figure out the salary. So we're going to take a look and see if we can come up with either a better model or do it a little bit easier, or who knows, even come up with the exact same model.
Awesome.
So what I'm going to do is I'm going to use Azure Data Studio for this, and this notebook is available on our GitHub page, which is on the screen right now, aka.ms/SOSN. That's something old, something new. That's our show. So let's take a look at this notebook.
I like that logo. Look at that. That's very nicely done.
Yes, our nicely updated logo, not little Buck's head with some glasses, but actually just Buck's head, which makes more sense. Okay, so this is also Azure Data Studio. I'm using the notebook capability. Data scientists love notebooks, and I really like the integrations in Azure Data Studio. I can do Python and all sorts of other notebooks. All right, so we're looking at linear regression, and the first thing you might want to do is import libraries. So just like Buck did in R, there are libraries that I like to use very regularly in Python. So I'm just going to bring those in now. But basically, NumPy is a very popular library for working with arrays. It's super useful. It has a lot of awesome capabilities. And same with pandas. Pandas is really great for data frames. So if you're doing analysis, data frames can be really useful. If you have series, pandas is really useful. And then this is one I haven't worked with as much. Buck told me about this one from the stats side. It's called stats models. And I took a look at this, and it actually has a lot in here. You know, Buck, I'm sure you've used this library a lot as well, right?
Absolutely. Yep. And you mentioned pandas. Pandas will make our DBA friends and our SQL Server friends feel right at home because it puts things, and you get indexes, you get tables, you get select statements. It's very nice. Yeah,
definitely. And I just want to take a pause just because the comments coming in are awesome. Master JX9 says cool logo. Thank you, Master JX9. I'm not sure if you saw the previous version of this logo, but it was very interesting as well. Jonescu7 says predictions to be, did Buck lose the bet or not? You missed the beginning of this, my friend. Buck did lose the bet. I won the bet. TBD on what the reward for that is.
Yeah. We got to get that. Yeah, I did lose the bet.
And then I think this is laughing. I'm not sure what this emoji is. That's what?
Let's hope so.
Oh, yeah, let's hope so. We'll take it off the screen now. Okay, back to our notebook. I just wanted to call that out. So
I like that. I like that libraries and NumPy, like Matplotlib forms the basis for a lot of other libraries, doesn't it?
Oh, definitely. You know, and everyone has their own pronunciations for this. As being someone who worked mostly by myself on data science or using forums online, I actually pronounce this Matplotlib. I don't know why. I don't know how other people.
Well, you're in California, so I think it's
you never know.
More liberal, maybe.
That was bad, but anyway.
And I remember when we had public libraries because we didn't have the internet, and so
you say live.
Matplotlib.
And I use Libby, which is an app where you can rent audiobooks for free. So Libby. Anyways, I digress, not regress. I'm not using that bad pun. Matplotlib, whatever you want to call it, is super awesome. We're going to take just the slightest of glances at this, but we've shared some resources for you to go a little bit deeper. So the first thing we're going to do is just bring in this data that you used as well. And the nice thing about Azure Data Studio is I can also actually take a look at this data. So we can see, Azure Data Studio is great for taking previews of data and stuff. So I can see it's very simple CSV data, salary, employed. Now, one of the great thing about pandas is you can read CSVs really easily. Now, NumPy, you can do it as well, but it's a little bit more verbiage. I just look for the least amount of code I can write and use that. And so
always best. And it even works with Excel spreadsheets. Pandas has a really good Excel spreadsheet library to be able to read just as easily Excel.
Yeah. So we can use this verbiage of describe to just get an overview of this data. So this would be a very light EDA or exploratory data analysis where we're looking at, okay, we have 74 items, just like you had mentioned. We can look at the mean of salary and years employed, look at standard deviation, and then some of those thresholds that you might see in something like a box plot.
And see those back to your point there, that standard deviation is really high.
Really, really high. Yeah.
So we know that this data is scattered. We can just look right here at one value and say that is really scattered.
Yeah, definitely. And okay, so let's see. So the next thing we might want to do is get our X's and Y's just to be consistent with the format we've been talking about. So our X is going to be our independent variable and our Y is going to be our dependent variable. So the thing that depends on the other things. And we say X1 here because it's possible that you could have multiple independent variables and you would have X2, X3, X4, depending on your scenario. So we can just go ahead and take a look at that. Now we're just seeing the actual values. This would line up with what we saw in the CSV files. Then now we might want to do some things with Matplotlib. So this was the abbreviation that most people use when they import it. So the interesting thing about Matplotlib is that you can basically stack what you want to do. So I can say, hey, give me a plot that's a scatter plot with X1 on the X-axis, Y on the Y-axis. Okay, add to that plot the X label, add the Y label, and we can take a look at that. Now, after I'm doing the scatter plot, I'm creating a new plot just by using plot show, and that's just going to connect all the dots together. So again, this first plot here, we have years employed, salary, we're just plotting all those points.
This looks like my Excel one. The difference here is it looks like your X-axis starts much better than mine did. You'll recall mine started at 0, 0 because of the way Excel works, and I didn't change it. And yours automatically kind of knew, hey, I'm just going to automatically set. So that's kind of nice. Right.
Yeah, it's nice. It looks at the range and tries to figure out the bounds. Now, this plot show just connects all the points. This is not useful.
No.
This is less useful than if you were to just put an average across, like a straight line. So we might not want to use this. But for example, just to see how easy it is to add X and Y axes here, it's really easy. You can just put again, plot X label, and then years employed. And then if you're really lazy like me, you could just do this, copy and paste it over. And now you'll see that you're going to have some labels for that second plot. And there's lots of other stuff you can do here. There's even other libraries that integrate with Matplotlib. You can make really nice visualizations.
Very nice. Much easier.
Yeah, very, very simple and nice to just kind of save it all in a notebook. Okay, so now we're going to use this stats model, and we're basically going to use this one command. And so what this is doing is saying, okay, use that least squares method, take in the dependent variable, the independent variable, and then fit it to the model. So we're going to fit it to the model and then give me a summary of that model. So very easy to do this. And now we're going to see some results.
Yeah.
So the top part of the results is going to be, information about the model and how it performed. So for example, we can see what the dependent variable was, what the method is, least squares. We see some other information like the number of observations. This DF residuals is the degrees of freedom, which is going to be the number of observations minus the number of independent variables minus 1. So interesting formula, but that's how we get to 72.
Okay, got it.
And then there's lots of different statistics that people like to see when they use a machine learning model to see how it performs. So this first one, R squared, which Buck talked about, is going to kind of say, okay, how much of the variance does this model explain? And you would hope for a model, at least above 70. So this is my first indication that maybe this isn't like the best fit or the best way to model this relationship.
Okay.
You also have adjusted R squared, which is going to penalize you based on the number of variables that you use. F statistics, some other things here, log likelihood, like you were talking about before. Lots of different ways to kind of analyze a model. And I would say with this model, some of them don't necessarily apply as much as they would in other cases where you'd be looking for things like overfitting or using too many features or that sort of thing. Do you have like a go-to statistic, Buck, that you look at?
So I often use something we'll see later, and a lot of these are on the screen here, but not in the right format, called the confusion matrix.
Yes.
And I think that's an interesting way to put it. And so I'll leave that to the viewers to go look up, but I often use the confusion matrix to find out how accurate and how precise the model is, because you can be accurate and you can be precise. You want to be both if you can.
Yeah, definitely. And there are even some more, like Durbin-Watson is a very popular one, skew, kurtosis.
So interesting on the skew and kurtosis, those often come out. We talked about this in our EDA. And as we were talking about in EDA, there's this standard distribution of data of a curve, right? And a skew and the kurtosis has to do you remember we talked about the right-tailed was really on the left and the left-tailed was really on the right and that sort of thing?
Oh, yeah.
They have to do with that. So as numbers, they're almost useless. The skew and kurtosis don't actually, it's hard to put that in your head. But when you plot those, you'll see the hump moving one way or the other, which starts telling you how much you can trust the tails and centers. Remember, we talked about in the EDA, the measures of central tendency and the variance. It talks to you about how much you can trust that.
Yeah, definitely. And so now that we kind of looked at it, what we can do is we can plot it again. So what I'm going to do is plot just like we did before. I'm going to plot that scatter plot. I'm going to create an equation for a line given the coefficient and so what you're seeing there, that's the slope. And you're also seeing the B. So this would be your B0 and your B1.
Oh, okay. So that's just the formula. And the Y hat kind of tells us that so this is where we got into that weird thing where statistics starts calling things by different names. For instance, if we have a sample, we use a bar over things, and we have a full population, we use an uppercase letter. So that's that Y hat nonsense. We're trying to show you as many different ways of doing this as we can.
Yeah, exactly. So then I can simply just like plot plots on top of each other. So plot the scatter plot, then plot that line and color it red and label it. And then you can also, just like before, you can add your X and Y labels. You can see we also added a font size, so we're making it a little bit bigger. And you can see now how that line fits or doesn't fit in there. And you can think about the OLS model and think about how far some of these points are from this line, and just kind of, you know, maybe see this isn't going to be the best way to model this. Maybe there's some other variables that we should be using.
That's what I'm thinking. I mean, if I looked at this right off, I'd say not a very good model, just not a very good model. And then secondly, I'd say, are we missing data? Are we not throwing outliers away? And then when you tell me, oh, I've got one independent variable, whenever you hear one independent variable in something, that's a red flag right there, because things are rarely that simple.
Yeah, I mean, more often than not, you have way too many variables. You know, we do a lot of, in school, I did a lot of high dimensional data analysis where you have thousands of features and you're trying to figure out which ones are important and how many should we move. So this is a bit idealistic that you would just have one variable.
Well, this is very cool that you showed us linear regression, and it's basically, scroll back up, it's basically that one formula you did right there. Are you sort of telling me that one line number 2 is, and I guess line number 1, that's what you do all day as a data scientist? That's what they pay you for?
Yeah, pretty much. And then, you know, when I see people using Excel, you know, so this is your same Excel spreadsheet that you pulled up, right?
Yeah.
I'm like, okay, this is cool. You came up with the intercept and the slope, but did you know that if you just do intercept and then you enter your known Y's and your known X's, this might be worth it. We'll see. You'll get the same number.
Yeah. So, okay. Nobody likes a smart aleck. Go back to
Excel behind the scenes is actually doing this OLS regression when you when you just say slow.
Now you're just showing off.
So you can really escape all this math and typos that ensue with just 2 formulas. So even if you're not a data scientist, you're not using Python, you could use this in your daily work. Pretty cool, huh?
You kids with your calculators and your internet, and I don't know.
So we have a few minutes left. I wanted to share, you know, you want to be careful about what you model, right? And we kind of saw that this one independent variable before didn't really work. Now, I'm a decently sized sports fan, specifically the Tennessee Titans. And anyone who watches sports, I know, Buck, you're a huge sports fan, knows that Derrick Henry has just been on fire.
Oh, yeah. I mean, he dribbles the ball so well, and then the putting. With his putting, I mean,
those are both the wrong sports. This is football we're talking about,
okay.
But I was scrolling on Reddit the other day and I saw this post, and so what they're doing here is they're doing, you know, this linear regression. It looks like in Excel, and they came up with a really high R² value. So this means, you know, it's covering a lot of the variance. What they did is they took the years on the x-axis. They don't have labels here, and they took the rushing yards on the y-axis. And they plotted that, and then they said, okay, based on 2016 to 2020, King Henry or Derrick Henry is on par to do over 3,000 rushing yards in 2023, which is just kind of crazy. So, you know,
imagine what he'll do in the year 2402.
I know, he's going to be like just a Hall of Famer just from existing. You know, he's going to be scoring record. I think we must get a Super Bowl win in 2023 then.
You'd almost have to, yeah.
We almost have to at this rate.
Whatever.
And someone thinks we're funny, so thank you. We try very, very hard to be funny.
I know.
Okay, sure.
Stop. This is math.
Okay, so I have one more example. I think we have some time for this. Let's see what's going on. Yeah, so this last example that I have is about logistic regression. So just to kind of bring everything home, you talked about linear regression, then you talked about logistic regression. Right. So I just wanted to show you a super simple example. Now, this is the iris data set. This
Yep.
is a data set that's just so overused because it's built in to sklearn. You can see, you can just get it. You don't have to go try to import a CSV or anything like that. You can just get it and start to play with it. So sklearn is great because you can get the logistic regression package, and it's really useful. So basically all I'm doing is I'm loading iris. You can see how I do that. And if I just run that, you're going to see the first 10x. And if you're not familiar with this data set, what it's doing is it's taking 4 measurements of a flower and then predicting which type of flower it is. So these are, well, it's telling you what type of flower it is. So these are the labels for all of these data points. So what you can see is like the first 50 points are one type of flower, the second 50 points are another type of flower, and the third 50 points are a third type of flower. So there's 3 types of flowers. And so what you might be wanting to do with logistic regression is to predict or classify based on these 4 variables. So we're taking in 4 features this time instead of 1.
Right.
Which type of flower is it? And with this, with sklearn, it becomes super easy because all I do is I create this classification model, logistic regression. I set the random state so I can get the same numbers if I want. You can set this to whatever, and then fit it to the model, just one line. And basically from that, I can take a look at some predictions of the classifications and also take a look at the probabilities. So what you can see here is for these 3 points I'm predicting, so it's a 0 flower, a 0 flower, and a 1 flower, we get these probability values. So for example, if I take a look at this first one, we see there are 3 values, and that's because there's 3 types of flowers, and we're saying, okay, what type of flower do we think it's most likely to be? So the way this algorithm works is it looks for the probability that's the highest. In this case, it's the 0 flower, and so the prediction is going to be 0. Now, if we look at the last one, we can look again at these 3 values and doing some comparisons, see that this value in the middle, or the 1 flower, is the highest probability. And so that's going to lead us to predicting.
I see. I see how that's working now. So it gives us a prediction for all 3, but it says, well, it could be a 0, it could be a 3. I think it's a 1.
Exactly. Yeah. And then we can also score the model. So super easy to do this. You don't have to do any of the hairy math that we kind of talked about earlier, and we'll share all these notebooks for you guys to play with.
And this is interesting because we'll show in the future. I think we showed in the first episode about the MNIST data set, which is just this data set of handwritten letters, and you had to predict: is this a 1? Is this an A? Is this a B? Is this a 7? And so on. And interestingly, what Anna just showed you there is very similar to that process. But there are different classification algorithms we can use. We've shown one today, but you should know this about this episode. Regression is probably the hello world, the select statement of the machine learning world. You can almost never go wrong by at least trying a logistic or linear regression to start based on the category of question you're trying to answer.
Yeah, definitely. A few things as we close out. Again, if you want access to any of these code samples, this is the URL, aka.ms/SOSN for something old, something new. We do have new episodes of Data Exposed live every Wednesday at the same time, so be sure to join us. And actually, this is kind of a rare occurrence, but Buck, you're coming back next week. Did you know that?
I am. Yeah, I do. It's an Ask Me Anything session, different than this show. This show we're running every month, once a year, because I only have 12 math shirts and 12 dad jokes. So we're running this one every month as something old, something new. But I do come on the show, the Data Exposed show, from time to time for other things. I think even Bob Ward shows up on your show from time to time, doesn't he?
Yeah, I mean, next week is going to be a really exciting episode because, well, it might be off the rails. Like, I'm going to have to figure out how to plan for this. We're going to have you, Buck Woody, of course. We're also going to have Bob Ward, and we're going to do an Ask Me Anything. Ask the experts any questions you have about SQL Server, about data science, Azure SQL, migrations, anything related to any of those topics, you're going to be able to get your questions answered live. And because I'm anticipating a lot of interest in this session, I did create this aka.ms, with my co-producer Marisa, and we're hoping that you can go to this URL and actually pre-submit your question. And if you pre-submit your questions, you're going to have a higher chance of getting your questions answered. But we will also be taking questions live, so you're definitely going to want to tune in to Learn TV same time next week. You know, we're nearing the top of the hour, so thank you all so much for joining us today. I'm going to put up our special thanks slide and pass it off to Marisa. And
right, before you do that, that's Ask BW. That's for Buck Woody, not for Bob Ward. I mean, obviously.
It's kind of for both, but yeah, we thank you for joining us, and we hope to see you next time on Data Exposed.
Thanks, everybody.
We'd like to give a special thanks to Wolfgang Pauli, Jeremy Reynolds, The French, Learn TV, Channel 9, the Tennessee Titans, and as always, produced by myself, Marisa Brazili, and Anna Hoffman. Thanks all. See you next week.